At the royal banquets of mid-19th century France, Emperor Napoleon III reserved his most prestigious seating for those eating with dull silver utensils. While standard nobility used solid gold, the highest-ranking guests were given cutlery made from a material then considered far more precious. This was element 13, aluminum. At the time, refined aluminum was so difficult to produce that it commanded a market price higher than gold, making it a definitive status symbol for the European elite. This chart of the Earth's crust reveals a strange contradiction. Aluminum is the most abundant metal on our planet, making up more than 8% of the crust, vastly outperforming the availability of iron, copper, or gold. The difficulty lies in its high reactivity. Aluminum binds fiercely with oxygen, which hides the metal inside a common reddish-brown rock called bauxite. Because early civilizations lacked the means to generate the chemical force required to separate these atoms, the material remained trapped in its mineral form for thousands of years. By the late 1800s, chemists were competing to isolate the metal efficiently. Early methods were slow and expensive, yielding only small amounts of pure material after immense effort. Charles Hall and Paul Héroult independently discovered that where traditional heat and chemistry failed, electricity could succeed. They proposed a process that used electrical current to force the atoms apart. Their method, still used today, begins by dissolving alumina into a molten bath of the mineral cryolite. Passing a powerful electric current through this liquid shatters the bond between aluminum and oxygen. The pure metal then separates and collects at the bottom of the vat. This process requires immense amounts of energy to maintain the necessary temperatures. Workers in heavy protective gear must manage these vats where the electricity and heat keep the metal in a liquid state. This discovery caused the price aluminum to drop rapidly, turning it from an imperial luxury into a primary material for global industry. This newly accessible metal offered a unique physical profile. It was exceptionally strong for its weight and naturally resisted the effects of corrosion. These traits made aluminum an ideal replacement for heavy steel in aviation, providing the lightweight structural integrity needed for aircraft to take to the sky. Modern aerospace manufacturing operates at a massive scale, utilizing these properties to construct the large fleets required for global commercial travel. Space exploration further pushed these limits, with NASA and the European Space Agency using specialized aluminum alloys to build hulls that can withstand the extreme environment of orbit. By making mass-produced flight and orbital travel achievable, the Hall-Héroult process provided the material foundation for the 20th century's revolution in transportation. In the modern era, the growth of cloud computing and artificial intelligence has created a new challenge: managing the intense heat generated by high-performance hardware. Aluminum's high thermal conductivity allows it to absorb and move heat away from processors with great efficiency. Data centers use aluminum heat sinks and structural racks to dissipate the heat from thousands of servers, protecting the infrastructure that powers our digital world. The metal also forms the core of the high-voltage lines that transmit electricity to these massive computing centers over long distances. While AI and digital services appear intangible to the user, they are physically supported by the thermal properties of element 13. While it is indispensable, the primary production of aluminum remains energy-intensive, and the mining of raw bauxite requires significant land use and processing power. However, the atomic structure of the metal allows for a sustainable alternative. Once it is refined, aluminum can be recycled indefinitely without losing its strength or quality. The efficiency of this loop is significant. Remelting used aluminum takes only 5% of the energy required to extract the same amount of metal from raw ore. This has created a robust secondary metals market, where millions of tons of material are recovered from products like beverage cans and vehicle components to be reused at scale. This recycled material now feeds the production of lightweight electric vehicles and sustainable infrastructure, reducing the environmental impact of modern manufacturing. From its origins as a rarity for emperors to its role as the backbone of modern industry, element 13 has evolved into a fundamental material for a sustainable industrial future.